So now that we have looked at where discontinuities on a rational function occur, we now need to start talking about what type of discontinuity it is. Like, do these discontinuities have anything in common? Do they all look the same? So go back, remember the function that we were looking at is right there. It's f of x. And some people had made the suggestion that we cancel out the common factor from the numerator and denominator. And we can see that in their work right here, because they said that x plus 1 over x plus 1 equals 1. So we can go ahead and cancel that out, right? It's not really going to matter. But I love the fact that some people who did this even started to question if this would cause issues. Matter of fact, one person said, did I lose solutions when I simplified it? The interesting quick answer to that question is, no, you didn't lose any solutions, you gained some. And we'll talk about that more in just a second. So what happens when we cancel this out? Well, it's better safe than sorry. Let's not just go ahead and say, like, yes, we can. And some of you might have already seen that there's an issue when we cancel out that factor. And again, here we can go ahead and just see that this is the factor they're suggesting that we cancel, right? Which would then lead us to p of x if we did that. And so rather than just go ahead and say, yeah, we can, it seems logical, let's do it. What if we looked at the graphs? And some of you did look at these graphs. So look at the graph of f of x on the left and the graph of p of x, which I'm going to call p of x. I'm going to call this the pseudo function, you know, like in biology when you're talking about like pseudopods, you know, false foot. I'm going to call this the pseudo function for f of x. That's not really a technical term. It's just one I like to use. So p of x is the pseudo function for f of x, the one that we got when we canceled out x plus 1 over x plus 1 right there. Okay? So when we did that, p of x is the function that we're going to get. So if canceling out the common factor caused an issue, then wouldn't the graph look different? And I don't know, Painter, to me, these graphs look exactly the same. So we're good, right? They look the same. But I found this quote by Friedrich Nietzsche. I believe that's how you pronounce it. And I love this quote for multiple reasons. It's basically, to me, what this quote says is that you need to step back. You don't just go with a snap judgment. Step back. Look at from every angle. Look at the issue from every angle. Don't just make your first thought or like quick judgment. Look at it from all issues and all sides and think about it from multiple avenues before you respond. Matter of fact, even in class, you can see I love this idea of one must not immediately respond to a stimulus. We want to step back and think first. So what if we do this? What if we don't say like, hey, the graphs are the same, you know, the graphs look the same, like we thought we could do this, the graphs look the same, boom. Let's look at it from all angles, right? All sides. Let's defer judgment. So what if instead of just looking at the graphs or the equations and thinking about them rationally, what if we looked at the table of values? And so on the left there, you can see the table of values for f of x. And on the right, the table of values for p of x. What do you notice? And if you were careful, you saw that we indeed did somehow change the function when we canceled out that common factor. Because the function f of x had 3 discontinuities, whereas the function p of x only has 2 discontinuities. So somehow we lost one of those discontinuities. And indeed, you know, You can go ahead and start to investigate this. So remember, when we were canceling out the common factor, we kind of ignored the case of when x is equal to -1. Because what if x equaled -1? What if we had put in x equals -1 right there? Or could you still make that statement right there if x was -1? I mean, think about it. If we put in -1 right here, wouldn't we have 0 over 0? And is that really equal to to 1 itself? If you don't know the answer to this, ask Siri. See what she has to tell you. Okay. The issue is x equals -1 was not in the domain of f of x. X equals -1 was not a possible input for f of x. But when we canceled out that factor, we ended up removing the problem that x equals -1 would have caused. This has no issue with -1. -1 would not cause an issue inside when put as an input into that function. But -1 would cause an issue in this function. Right? And that's the issue. We ended up removing the issue. But doesn't that actually change the function itself? So the question becomes, what does this all mean? Right? Are the two functions really the same? And the answer is yes and no. Right? I mean, go back and look at the graphs really quick. Do they look the same? Yes. Do the tables look the same? Yes and no. Right? Everything looks really good. Except, right, like, and I could keep doing this all day long, except there does seem to be this weird issue. Where is that weird issue? It's right there. So are the functions the same? Yes, mostly. All the blue stuff. Matter of fact, everything. Except no, because of that one purple spot. Right? So we looked at those graphs again, right? Like, we can see they look exactly the same except for at that one spot. You see it? You see that one spot? No, of course you don't. Okay? You can't really see it, right? The graph isn't showing it, but it is there. Okay? So when we canceled out that common factor, we removed a discontinuity. And so the functions are no longer truly the same. They're just really, really, really similar. Like we said, the function f of x has 3 discontinuities. Okay. One of them happens to be a removable discontinuity. Why is it named that way? Because we removed it. Matter of fact, that removable discontinuity is also called a hole or a point discontinuity. Okay? And if we zoomed in close enough on this graph of f of x over here, not the graph of p of x, if we zoomed in close enough, what we would see is like it's going to be really hard for, right there, we should see a little tiny hole, a singular missing point. Point, not like a big section that's missing, but a point that's missing, right? I mean, this is as small as like a grain of sand, smaller than a grain of sand, which is why we don't see it. And so I really want to show us, like, on the graph, what they would do is they would draw an open circle at that point. That's what mathematicians do. We draw an open circle at that point, and that indicates that, hey, like, yes, we like this graph, but at that one spot, there is something missing, okay? And so they would trace the rest of the graph, right? And I could keep going, but I'm not going to. But at that one spot right there, oh, I filled it in, bad idea. Don't fill it in. It's an open circle. That point is missing on the graph because it was a removable discontinuity. It's a hole in the graph. And then, also we can see that there are vertical asymptotes, things that we have talked about before. There seems to be a vertical asymptote right there, and there seems to be a vertical asymptote right there, right? And we already saw kind of where those came up. So again, the graph is going to look different in this. This is a graph on Desmos. Desmos doesn't do a great job showing the hole, but we need to when we draw it, all right? But the interesting thing is, if we were to graph P of X, right, like go back and graph P of X wouldn't actually have that hole. P of X would look really like that, and there would be no hole on P of X because we removed the discontinuity when we made our function P of X. So it's a hole on the graph of f of x, but once we simplified it, the hole isn't there anymore, right? We kind of filled in the hole. We removed the discontinuity. So just to recap, there are three main types of discontinuities. There are jumps, which often occur in piecewise functions. There are holes, which, are discontinuities that we can somehow remove or cancel out the issue. Or fill in the issue, right? And they're often on rational functions, but they can occur elsewhere. And then we have vertical asymptotes. These are non-removable. You can't cancel these out. These are infinite discontinuities. And that name is clever because if you go back and look at the asymptotes, right, you can see why we might be calling those infinite discontinuities. But we'll get to that later. So a great question that leads off of this is, why does the graph look the way that it does around each type of discontinuity? And this is a wonderful question that we will explore as we move forward.